Go right ahead.
Okay, today we are fortunate to have with us Chris Wiggins, professor of applied mathematics at Columbia, chief data scientist of the New York Times, founding member of the Data Science Institute at Columbia and the Department of Systems Biology. Also a longtime old friend of mine from the graduate school days, which I was going to say was the 20th century, but he points out is actually the previous millennium. So we've known each other a long time. And he's going to tell us about building better bandits, as sort of online reinforcement learning approach to decision making. Thanks, Chris.
Of course, it's a pleasure to be here. Yes, so as advertised, Steve and I knew each other in the previous millennium. I had the pleasure of meeting Steve when he was about to be a freshly minted PhD. I was just starting my PhD work in theoretical physics at Princeton, and then learned a lot from him over the years when he stuck around at the NEC, which was a hotbed of information theory and machine learning in Princeton in the 90s, and later at the Institute. So it's been a pleasure working with Steve to set up this talk. Right, so also as advertised, I'm splitting my time between Columbia and the New York Times. Today, I'm going to talk about some things which, although somewhat inspired by work at the New York Times, are really quite solidly work done at Columbia and research and innovations. And also, Steve and I talked about how many people in the audience now and in future webcasts will likely be coming from a physics background. So I'm going to talk in particular about ideas from physics, which particularly statistical physics, which turn out to have applicability in some of what I think are the most interesting current challenges in reinforcement learning, a particular branch of machine learning that's having very broad impact, particularly in industry, but also some other fields that I'll talk about. And with that, so I'll talk a little bit about, again, anticipating an audience trained like me and Steve coming from a theoretical physics background. I'll say a few words about what even is machine learning and how do we think about reinforcement learning as a particular sort of city within the continent of machine learning. I'll introduce reinforcement learning as a type of optimization, and then getting into things that I think those of us coming from statistical physics will recognize. I'll talk about how you might adopt some ideas from statistical physics to try to advance this problem and also build actual working algorithms that people use. Some of these approximation methods, I would say, also come from the applied mathematics literature, my own now professional literature. And in particular, variational methods, which physicists know by different names, but it's a suite of methods which has had a resurgence this millennium in the machine learning community. And then Monte Carlo methods advanced immediately after World War II, which remain useful in a wide variety of fields. And then some invitations to think about things that might be of interest to you, the audience, either in research or industrial contexts. So machine learnings.
Chris, can you just remind everybody that there is a Q&A feature so they can
yes.
submit questions, but we will only be getting to them at the end.
Absolutely. So although I've been Zooming talks for about 15 months, I have not yet acquired the ability to talk and read at the same time. However, Steve, I encourage you to interrupt at any time with questions, and then we'll have more time for Q&A at the end. Good. So my training was not in machine learning in the 90s. So let me say a little bit about machine learning. What even is it, at least as we understand the term today? And then I'll talk about different types of machine learning so that you know a particular area of machine learning I'll be focusing on today. If you go to most popular websites and ask what is machine learning, they're going to talk about a particular problem, which I want to emphasize is a subproblem of machine learning, which is the ability to discriminate two different things. A canonical example, and this is from an industrial website, I just went to Cisco and said, what is machine learning? And they said, well, supervised learning is one particular subproblem of machine learning for telling whether or not a particular image has a cat or a dog in it. And it's true that if you pick up a newspaper or click on a internet website today about what is machine learning, the headlines you'll see will probably about this problem. Do you have sufficient data from prior examples where there might be many, many attributes or features, like everything that's in a picture, and then you really want to predict just one thing from all of those attributes? often just a binary thing. Is it a cat or a dog? Is this cat face or dog face? Most of the headline generating things in machine learning are of that flavor. It's a straightforward prediction problem where future data will be drawn from the same distribution as past data. And machine learning in the last decade has gotten very, very good at that. As a statistical problem, it dates back to the 19th century, but techniques for doing this computationally at scale with big data have gotten very, very good. And that's driven the lion's share of, I would say, hot press for machine learning in the last decade. Also, it's got cat faces in it. But that's just one flavor of machine learning. So going to another industrial website, which again, it'll be interesting for historians to note how the history of this field was written by like marketing materials on various .com websites. You can go to MATLAB's website. I spent a lot of time in MATLAB in olden times. You can go to MATLAB and ask MATLAB, what is machine learning? And it'll tell you there's two flavors of machine learning. Supervised learning, which is what I just showed you before, where you really want to predict one thing from everything else, and unsupervised learning, which includes clustering. So if you've ever heard of k-means or I don't know, Gaussian mixture models, or you can just imagine that you have a lot of data, but you really want to say, these data look like they're in 2 different groups, 5 different groups, or k different groups. That task is called unsupervised learning. It's in some ways more common because often somebody just hands you a big data set. They don't tell you that within that data set, there's one particular attribute, and I want to predict this attribute from everything else. They just say, golly, it would be nice to have a simpler understanding of these data. Said in other words, unsupervised learning is sort of a task of describing large data sets, and supervised learning is really a task of predicting something within a large data set. But it requires that you've done a little bit of work because you've decided what is the thing that you want to predict from all the other things. And things that you were probably raised with in the natural sciences, like regression, can be seen as a special case of supervised learning. So the cat face problem, regression, those are both types of supervised learning. Unsupervised learning, in which you don't have a label on every example, but you simply want to make a simpler description, is unsupervised learning. And so for most people, that is the extent of machine learning. There's two flavors. Also things that you may have heard of, like PCA or ICA or MDS. Those are also types of unsupervised learning under the name of dimensionality reduction. Or maybe you're a software developer, and so you don't go to MATLAB, you go to Python. So you go to the scikit-learn website and you ask it, what is machine learning? And it says, here's the types of machine learning. On the upper half is supervised learning. On the lower half is unsupervised learning. And for many people, that's it. That's all the machine learning is those two flavors of machine learning. And either you're trying to work with categorical variables, in which case you're on the left-hand side, or you're trying to work with real variables, in which case you're in the right-hand side. That's it. So one of the things I want to introduce you today is a whole third flavor of machine learning, which is really around prescription rather than description or prediction. So descriptive problems in machine learning are those where you have a bunch of data and you want to learn some simpler description of the data. So you have X and you'd like to learn Z, or maybe a probabilistic assignment, P of Z given X, where Z is somehow simpler than X, like a dimensionality reduction technique. So once you've done SVD or PCA or whatever you want to call it, that is a descriptive task. Many problems, you really just want to predict one thing from all the other things. So somebody hands you X and Y, and you want to predict Y from X. So in some ways, we've done a little more work because we've said, not only is there a table, but within that table of examples, there's one column that's more sacred than every other table. However, when you leave the natural sciences and move into fields of application like healthcare or robotics or all of industry, often what you're trying to do is actually make a decision. And so you don't just want to predict the outcome in the absence of treatment. You actually want to know what is the optimal treatment that's going to maximize the outcome. Those are cases that I would call prescriptive problems. So those are problems in which the data that you're handed are not just a set of things that you're allowed to know before you make a decision, not just another column, which is what happens after you made a decision, but an even more sacred column, which is what decision did you make? And so there's a set of machine learning techniques and statistical techniques that I'll call prescriptive problem because it's a normal word in English, but roughly they map onto a machine learning field called reinforcement learning. Note that these are not things where you want to predict just the outcome in the absence of treatment, but you want to learn the best treatment, just to emphasize that point. The fact that people treat them the same has a long history. I'm a fan of history, so the idea of conflating correlation and causation goes way back. This is actually a paper from 2 millennia ago, at the end of the 19th century, when Udny Yule wrote this paper about why people are poor, and he called it an investigation into the causes of the changes in pauperism, and he answered it using multivariate regression with 4 variables. The coefficient associated with giving people help and the number of poor people being positive, he concluded that helping people causes poverty. So that is the correlation, the conflation of correlation and causation goes way back. But as we know, correlation is not causation. The problem, of course, is that causation causes correlation, which is why they're correlated. So it's hard work because you actually have to do an intervention if you want to understand what is the best treatment. That said, is really valuable. So it's more work if you have some system like your business and you need not only to observe what people do on your website, but you actually want to intervene. That means that you have to choose not only what is the thing that you want to predict that people are going to do, but you have to choose what is the intervention set that's of interest, like what is the set of actions, and then you have to actually do that in order to learn. So it's more difficult, but it's also more valuable. And here I'm just stealing from management consultants. This is a slide from Gartner, who does management consulting, and they tell CEOs what to buy or believe, I guess. And they say that the prescriptive problem is up and to the right. It is both the most difficult and it is the most valuable. A friend of mine who said this to me actually does reinforcement learning. And he said, I like this slide because my stuff is both the most difficult and the most valuable. You'll be hearing the words reinforcement learning more and more. So a lot of buzz of reinforcement learning has been just in the last, I would say, half decade. A good example of early buzz was this Nature paper by DeepMind before they became Google DeepMind. And they showed that they could get reinforcement learning to play Atari as well as a human being. Atari is like Nintendo, but from the 80s. Anyways, you can get a computer to play Atari as well as a human being. A point to note there is that you can do that because you have all the data you can eat. You can just make the computer play Atari all in all, and you can go to sleep and it will have played Atari all night for you. Real world applications are one where you have to wait for your data because you have to interact with human beings or some other system. And so this is a particular case where you, it's kind of not surprising that these techniques work first on games. Not unlike another historical note, the original usage of the phrase machine learning, which from a 1959 paper by an IBM researcher on the game of checkers. Anyways, now it's become part of their marketing materials. You can go find out about not just reinforcement learning, but deep Q learning. It's a whole thing. So it's getting buzzier and buzzier every day. In 2018, as sort of an extension, even cooler, is somebody showed that you could beat Atari not by trying to maximize the score, but just trying to maximize surprise. So you can do a reinforcement learning approach to playing Atari, where the thing you're trying to optimize is the probability that you didn't expect correctly what was going to happen when you did a certain thing. That turns out also to be a winning technique in games. That said, often game designers make things such that the way that you win is also fun and surprising and keeps you doing it. Anyways, it was pretty cool. And oh, I should say the other cool thing about this. Sorry, the thing that was really mind-blowing about this paper was when you come from the natural sciences, you think your representation of the world matters. Like when you work in computational biology, you think, oh, it matters that I represent sequence elements in terms of 7 mers because that's how big the transcription factor is going to be when it gets into the 11 nucleotide major groove of the DNA or something like that. So you think that the way you represent the world matters. In this paper, they just took the raw pixel values as the features and just input into a deep neural net. So so I should say part of the buzz in reinforcement learning that this paper provided was it's pretty cool for computers to beat Ataris, particularly if you played Ataris when you were young. But the other thing that was cool about this paper was we who grew up in the natural sciences would like to believe that domain expertise and feature representation matters. There have been many problems where you just give the machine raw pixel values, just every single pixel in an image, and it's able to beat you. So that was pretty mind-blowing. Oh, and I already made this point that machine learning itself as a term of art comes from getting machines to play games. Now, it's not just Google. So often those of us who are not at Google think, golly, those Googlers, they have all the data and all the computers. But these are techniques that even startups can use. So just to convince you that this is a set of techniques that work well, even outside of the Google, this is a blog post from Eric Colson's team at Stitch Fix. Stitch Fix is a startup that I think since you closed, I have to confess, I've never used Stitch Fix, but they're very nice people and they have a very good data blog. So this is a blog post for them from 2018 about how they used a particular approach called contextual bandits, which I'll talk about today, for personalization. So personalization is another example where it's not that you particularly want to predict how many people are going to click on different links. You really want to know which link should you show which person in order to get them to, you know, buy clothes or click on things or whatever is the response that you're trying to optimize. In fact, as I said in the beginning of this talk, I'm going to talk today about Columbia research, not New York Times things that sort of inspire this research, but the New York Times also does use reinforcement learning for algorithmic content recommendation. Since 2018, we've been using contextual bandit approaches to, within very limited pools of content and within very particular surface elements, recommend different items to different people. And there's a nice blog post about that on the New York Times open website if you want to read more. I should also say, it sounds like this is just something for e-commerce or for internet website homepages, but it's also something that's appearing quite a bit in the health context. I mentioned in the beginning, in the natural sciences, you often don't want to make the system do something, you want to understand the system. But in healthcare or robotics or industry, there's many times that you actually want to optimize something. So Susan Murphy is one person who's been looking at reinforcement learning for health. And you can see it having rising impact here. I'm looking at citations to the phrase adaptive clinical trial, which is an example of changing the probability you give somebody treatment over the course of a randomized controlled trial because you figured out that one of the treatments is actually more effective and you want to optimize treatment en route. Right, adaptive treatments or adaptive interventions. So that was the search query that I did to generate this graph. Okay, I mentioned the term bandits. Now, if you grew up in the physics context, you probably haven't worked with bandits as a technical term of art. Why would you talk about bandits? So the phrase itself comes from the term one-armed bandit, which is one euphemism for, or one synonym for a slot machine. So a slot machine takes your money, so it's like a bandit, and it only has one action. You just pull one arm. But let's say that you imagine yourself at layover in Las Vegas, and you're at the airport, which is a terribly noisy place, and there's slot machines everywhere, and you have a bag of quarters and half an hour, and you want to make as much money as possible. So as a statistical problem, you have to decide which slot machines should you put your quarters in. They probably don't take quarters anymore. But anyways, the last time I had a layover in Las Vegas, you could put quarters in things. And you don't really care how bad are the bad arms. So it's not like a maximum likelihood problem where you want to understand the system. It's an optimization problem. You're trying to make as much money as possible. And the abstraction is often made in the context of a finite time horizon, like you got 100 quarters or you got half an hour. So often the abstraction is framed as one where there's a finite problem and extent, which again is different from the thermodynamic limit or other problems that we've thought about in growing up as physicists. But anyways, that is why this problem is sometimes called a bandit problem, is because the slot machine sort of abstracts away, like I can only do one of like 2 or 3 things, and I'm not trying to do maximum likelihood and learn the nature of the system. I'm just trying to optimize something. You might ask, well, are they so different? Like, is the prediction problem really that different from the prescription problem? And in fact, one of the ways that people often deal with this in natural context is to simply learn a model that does regression, and which action you chose is one of the features. So you can do that by trying to learn a prediction function, and I'll talk in a minute about one approach that just does that. Then you would say, well, the optimal expert would just say that for any context, like let's say X is whether or not somebody comes in to your website from Facebook or from search or from some other context that you know when it's time to make a decision. Then you could choose the value of the action that maximizes this prediction function. This is one way of getting at that. However, just to get back to my earlier context, if you really have observational data you really don't know if the action that you've taken in the past was somehow correlated with X, in which case you have the potential totally to confuse yourself because, like, let's say the medical context, let's say you've got a bunch of medical records. Turns out that doctors have only given the expensive medicine to people who are already, pretty fit. It can look like the expensive medicine is highly effective, but really there was a correlation between A and X. There's a correlation between which action was given and context that was known before the treatment was assigned. So that, again, just a meta level point is reinforcement learning is particularly useful if you have a context where you actually can do interventions. So you're a doctor and you're willing to obey the algorithm, you work at a tech company and the people in product are willing to collaborate with the data science group or something like that. But it's much better to have things where you actually can break the correlations between action and context. Other ways of reducing them into each other, there's a nice approach, and there's a literature by John Langford at Microsoft Research, among others, where as an abstraction, you say, let's say minus here means I used to work at some other hospital. Let's call that the minus hospital. And people walked in the door and they presented symptoms X, and then I gave them drug A, and then they responded with response Y. So as a probabilistic description, let's just make up new variables for that. I'll say they responded with response function R. I assigned drugs to them with the policy pi minus, and they came in from the world described by some distribution W. In what I've written down here is an important causality assumption. It's the assumption that when I move to a new hospital, let's call it the plus hospital, that people will come in from the world the same way. So it'll be drawn from the same distribution of world or whatever you want to call it, W. And they will respond the same way. That is, they will have the same biophysics, even though it's a new hospital. And so the only thing I will change is the policy, which is why the subscript plus and minus changes and moving from the minus hospital to the plus hospital. So there's a causality model there. You feel like I should be able to learn something from the amassed electronic health records of the minus hospital, which will help me give better policies in the plus hospital. How do I think causally about that? One way is to obey the rules of probabilities. So you write down the probabilistic description. You're saying I'm going to make the policy change, but some elements will not change. And then I apply multiplying by 1 in the form of something called important sampling, meaning in my new hospital, I will compute this expectation under the distribution P plus, but I have taken data that are sampled from P minus. But the only thing that changes between P plus and P minus is the policy. So a little bit of math, you follow the math and you get a technique, which I think is called the Horvitz-Thompson estimator from 1952, if I remember correctly. But it's a basic idea that if I want to estimate how good a policy is using data from the old policy, all I need to know is what their policy was and what observations they made, and I can use that to train a new policy. So Langford, among other people, has said, well, you can reduce the problem of learning the best policy to one of multi-class classification. That is, you can rewrite this algebraically as a weighted multi-class classification problem where you're trying to predict for the new hospital, what should you do to people? And there's a lot of literature on this. If you see literature from statistics, this is called the inverse propensity weight. I'm not promising you that learning the multi-class classifier will be easy, but it is an algebraic observation. So the algebra works. I'm not saying that the statistics and the engineering will work, but there is one literature in which prescription is framed by reducing it to multi-class classification. One special case of this is itself the randomized control trial. So maybe you're lucky and the old hospital, the P minus hospital, just gave random drugs to random people. There's K different drugs, and so they gave those drugs with probability 1 over K. So that's an example of how a randomized control trial context can be useful for deriving or learning the optimal policy. And there's a bunch of good literature, often by people from Microsoft Research, actually, about how you can learn exploration data in order to learn the optimal policy. Right. And that gives you a way of estimating how much response or how much reward you will get under the new policy for given old data. Okay, I don't want to talk too much given time about special cases, but trust me, the math works. All of this, though, assumes that you actually did an intervention. That is, it's very difficult to know, say, what was the policy in the old hospital. And worse is if you just have observational data, you need to infer what possible conflation was there between action and treatment. And that's really what's going on in this Udny Yule paper from 1889. He's basically looking at different regions in England. And yes, the regions with the poor people are also the places where there's more assistance for the poor. They're highly correlated, but that doesn't mean that the existence of places to help people with their poverty is causing the pauperism, despite the fact that he put it in the title of his paper. A fun fact is that, yeah, and there's a nice, if you want to read more about this, the late David Friedman wrote many, many great papers about how to think about the world statistically. One of his papers was this one, pointing out, as he put it here, the coefficient being relatively large and positive, Yule concludes that outrelief causes poverty. Outrelief meaning giving people money rather than putting them in the poorhouse. Anyways, it's a nice 2014 paper. Yule knew it, by the way, just in defense of Yule. He hid it in a footnote. So you can go look at footnote 25 where he says strictly for due to read associated with. You see things all the time like this in the real world. For example, if you, an example that Duncan Watts told me years ago is marketing literature where people will do less advertising during most of the year, but then they'll do a lot of advertising at Christmas time, and then they'll get a lot of sales at Christmas time. And dividing the coefficients by each other, they say, now we know how efficient advertising is because we know how many more sales we got at Christmas time. And we also did more advertising then. Okay. I don't want to besmirch Rutherford because this is a physics audience. Instead, let's talk about how you would actually do this. So let's talk about reinforcement learning and let's actually talk about some math. There's a couple of ways to do this. I mentioned earlier the idea of randomized control trials. This became canonized in the statistical literature in the beginning of the 20th century. You know, works like R.A. Fisher's 1926 book about design of experiments, or was it field workers? You'll have to fact check me on the title of his 1926 work. It was a good example of saying to people, randomized control trials are a good idea. In his case, he was trying to figure out for growing crops in England, should you use, I don't know, pig bones or cow manure? I mean, the action set was very different than showing people red buttons or green buttons, but that was a context in which he advocated that if you really wanted to know what works, you have to do things at random. Right, Fisher, 1925. In industry, this has been partially accepted. So in industry, you'll hear people talk about an A/B test. What they really mean is use science. Sometimes it's called a multivariate test. In some cases, they will actually use the term randomized control trial like you would use in medical communities. But there are places in industry where people are realizing that if you want to know the effect of a treatment, you gotta give the treatment at random. Otherwise, you're simply going to learn what the correlations are between the treatment you've been giving and the people who were getting that treatment. Now, the downsides to this in industry are that you have to take a meeting, meaning you do random things to random people, you run an experiment for a day or a month or a year, and then you have a big meeting, and then people say, ooh, this treatment did better, but what are the other downsides? And then you have to talk. And you, in the meantime, you're losing a lot of money or health or whatever it is you're trying to optimize because you were giving this random thing that at the end of the year, you found out was really kind of worthless. So a different approach would be to go with the winner. So you have to explore and exploit at the same time. You have to try different things out, but somehow gradually upweight the thing that seems to be winning. If you're going to do the explore first and then exploit, you have to wait until you've met a particular p-value. Again, this is an idea from Fisher and other great ones at the beginning of the 20th century of a particular heuristic for when statistical significance has been met. In the interest of time, I will not give a talk about the downsides of epistemic downsides of p-valueology. Instead, I will just point to the statisticians. So the American Statistical Association had this nice essay in 1926 saying, maybe we've gone a little too far with the p-values. So if you're concerned that there's too much p-valueology, you can use this asset from the statisticians themselves to back you up. A faster way would be to try to upweight the probability that you do the best thing as you learn what thing is the best. Now, the problem is there's no one right way to do this. So just briefly, I'm going to show you 4 different, very simple ways of doing this. And quite possibly, this will be the most valuable slide because the ways that I'm going to show you are so simple. They're all like one equation long, and you can go try them out, whether you're a doctor or a person with an internet website homepage or moneymaker or whatever. Here are some very simple ways. The simplest way is do the best thing, but with probability epsilon, just do a completely random thing. Surprisingly, this works. So this technique goes by the name of epsilon greedy. Mathematically, it means that the probability of doing thing A is with probability 1 minus epsilon, you do A because it was the argmax of the empirically observed mean return. But with probability epsilon, you just do completely at random one of the k things that are available to you. Note, it works in the sense that it does pretty good, but if you really want it to do good, the best thing is for epsilon to have sort of an annealing in which epsilon is allowed to decay with 1 over time, 1 over t decay. And there's a whole literature about what is magic about 1 over t. I mean, again, like I'm not showing you any sort of fundamental statistics, so it's sort of an exercise to the reader, depending on your appetite for reading mathematical papers. But it's pretty cool that something so simple as this, with this extra sort of heuristic idea that anybody who's seen annealing before would accept, that as you learn better, you would expect that epsilon should get smaller. And eventually, you just say, "Yep, this is the best thing." Tends to work pretty well, and this is very easy to code. Another way of thinking about this problem, which is deterministic, meaning that the policy is purely deterministic, you don't do things at random, is called the upper confidence bound technique. And most of this literature on this cites a particular paper from 2002. But the idea is I look at all the things I've done in the past, and for each one, I look at the empirically realized return of each strategy. Here they're called A for arms, or action, if you like. But for every technique, I will add to it the width of the confidence interval. That confidence interval scales like 1 over root n. I introduce another term which grows in time in a way that sort of penalizes excursions. I will not tell you the probabilistic bounds that motivate this, but it's distribution-free bounds, meaning bounds that make don't assume that you know the distribution from which the data is drawn. So it's a particularly pessimistic way of doing it, but allows you to do things that are, so to speak, model-free. You don't have to assert that you know the probability distribution from which the return is drawn. So I'll choose the thing that maximizes this quantity, which is not the mean return, but the mean plus the upper bound of the confidence interval. So intuitively, that's good because if I keep doing this thing over and over again, the confidence interval will shrink in time, like 1 over n. And eventually this thing will turn out to be the true winner, or its error bars will go down so much that the confidence interval of the second best thing will prove itself to be the thing I should have done. This is a deterministic technique because I don't do random things with random probability. I just do the thing that has the highest value of this confidence interval. I've used a particular notation for this, which is the bracket. It's a bracket is 1 if the statement inside is true and 0 otherwise. A technique that was published last year, although it itself draws on a nice paper by Phil Long and a co-author from 1999, is called, I'll call it IGW. So instead of inverse propensity weight, this is inverse gap weighting, which says, let us say that I actually try to learn a model of the world. So I'm willing to write down a function that says the mean return given any action A, possibly in the presence of some context, meaning attributes of the user or the patient or the world or whatever I'm allowed to know before I make a decision. I will try to learn directly by regression or deep learning, whatever you like, a function that predicts the mean return for every action. If I can do that, then I will choose the suboptimal predicted action, meaning once I have a regression function, or maybe k different regression functions in this case, that can predict my expected return for every action, I will do the second best or third best thing with a probability which decreases proportional to the gap. So the gap is the difference between your predicted return if I did thing B and thing A. So let's say that A is the thing that we all agree is the best thing based on my current model of the world. Instead of doing thing A, I might do thing B. And the probability I do thing B is 1 over a constant plus a learning rate times the size of that gap. Again, just like epsilon greedy, it's very simple to state. It's simple to write. It allows you to decide later what sort of regression function to use. And yet it turns out that this works. And works in this case means there's some nice papers, again, by John Langford and others at Microsoft Research, where they effectively do like a big bake-off of all the hottest contextual bandit algorithms. And this one seems to be, with some subtle tweaks, consistently beating everything else. And this is by publishing timescales hot off the presses, meaning it was published last year. But a different approach, an approach that's going to motivate my work for the next couple of slides, is very old. It's from 1933. It's called Thompson sampling, and it basically means use probability. So the idea of Thompson sampling is choose the probability you do thing A or action A proportional to the probability that A is the best thing you could have done. So what's the probability that A is the maximizer of your return, given all the data you've seen so far? So this is a very general and intuitive way of thinking about the problem. The hitch is you have to be willing to make a model of the world. Now, if you come from a modeling background, that's great. We like making models of the world. And in particular, you have to be willing to make a probabilistic model of the probability of any return given any unknown parameters. So when you make a model of the world, there are always parameters. And you have to be willing to write down a distribution from which those parameters are drawn. It might bother you, but some people call that being Bayesian. If that's a problem for you, there's 3 other charts, 3 other algorithms on the board you can take. But if you're willing to write down a distribution from which you think the probabilities are drawn, then this is a very simple and interpretable technique. And because it uses those rules of probability, which have been around for a couple of centuries, we get to leverage all of our understanding about how to deal with and approximate probabilities. Right. And note that in some of these algorithms, mu is the empirically observed mu. But in this case, mu is actually some algebraic expression given your model of the world and an unknown parameter setting. That sounds a little highfalutin, so let me make it really concrete by a particular example. This is just a restatement of the Thompson sampling algorithm from 1933. To compute this integral, the probability the thing is the best, I have to integrate out over the parameters, or algebraically equivalent, I can sample from the distribution of parameters, and then given the parameter setting, I know which arm is the best at that parameter setting. And so I simply choose the arm that is best for that sampled parameter setting. Again, that sounds a little highfalutin or a little abstract, so let me make it concrete. Let's say that there's 2 slot machines and they either give you $1 or they don't give you $1. So 2 arms, 2 outputs, simplest possible context. And in that context, the only sufficient statistics you need to keep track of are the number of successes for each arm and the number of failures for each arm. That's your data set. The outcome is either yes or no. So then the response looks like a Bernoulli distribution. That is, I'm willing to write down a probability distribution. You would be wise to choose your prior distribution for the parameters to be a beta distribution. It is the algebraically equivalent distribution, in which case your hyperparameters simply augment the observed parameters. And then you repeat. So you sample values of theta from the associated beta distributions. Given your thetas, you choose whichever theta is best for that sample, and then you repeat. It's pretty darn simple. And then the world increments for you either a success or a failure, depending on which arm you chose. It's wildly general. So it's particularly people who like interpretable generative models. You could write down a probability, whatever probability distribution you could write down for the probability somebody gets healthy, given the drug I gave them, anything I knew about them, and all the parameters that go into that model. It generalizes that A doesn't necessarily need to be categorical variables. The bad thing about it is that you have to compute things if you actually have to do the math. So you may have posterior distributions, probability of theta given the data, rather than probability of data given theta, which are difficult to compute, right? They involve partition functions in the denominator, which are a mess. You can't always compute the expected return, right? That is one more integral to be done. And another thing that I'll talk about is that the process might change and the values of these parameters might change, right? For example, if you're in the news business, the news is always new. And so you need methods that allow you to be dynamic. The other problem is that you might be wrong. So like the real world is never, the real world is outside of your hypothesis set. So in all of these techniques, you need to include the possibility that the world is simply misspecified by your model. This is also true, by the way, for the IGW, the case of the inverse gap weight. You know, the methods only work well if f, lowercase f, as I wrote it, turns out to include the true model, which the world never behaves like a model, in my experience. Good. So let's leverage statistical physics because a bunch of great ones in the 20th century worked really hard to figure out how to approximate posterior distributions. Let's leverage that. In particular, let's leverage some approximation methods. So one way to deal with this is to think about not Thompson sampling straight, but something I'll call variational Thompson sampling, which is a variational approximation to drawing from the posterior. If you were ever raised with mean field theory, they probably didn't teach you mean field theory this way, but mean field theory itself is derivable as a variational approximation to computing a partition function. This generalizes into a much more class of variational methods in which you have a true distribution and an approximating distribution. I'll make a historical interlude about this. But you can do this in Thompson sampling, for example, whatever model you like, including, for example, returns that are a mixture model. So it may be that people who come to your website are two different kinds, and some of them like to see this kind, and some of them like to see that kind. You can generalize it to pretty complex problems. You can also do this in a case where you don't know that there's too many people, two different people as opposed to three different types of people. And you can learn from the data how many types of people are there. You could also do this using Monte Carlo methods. If you don't like calculus, you can do this as a simulation technique. Let me include a historical interlude about Monte Carlo. But the key idea is take the prior results that you have and don't throw them out, but simply reweight the importance of those results as your understanding of the world refines. So mean field theory, this is a physicsy crowd. Certainly Steve and I are physicsy. When I was young, somebody told me Ising model. Let's approximate it by m prime equals tanh beta m and just iterate that over and over again. But they didn't exactly tell me why to do that. There is actually a variational idea underlying there, which is you'd like to compute a partition function, but you can't compute it, but you can bound it and then extremize the bound. This was known to Gibbs in 1902. He wanted to compute the expected value of the logarithm of this function, but he realized that was always bounded by the logarithm of the expected value of the function. So if you're trying to compute, let's say log of expected value of log, why not instead bound it with some free parameters and then vary those parameters to extremize the bound. Later, this gets called the Bogoliubov inequality in the physics community. But in statistics, people look at that and say, okay, well, that's just Jensen's inequality from 1906. So it's an old idea, 20th century idea, but still old. When you took statistical physics as a first year graduate student, they said, oh, well, use a test Hamiltonian. It's really the same idea. The test Hamiltonian is the approximating distribution with free parameters that you vary in order to extremize the bound. So as an example, let's say you wanted to compute a partition function, the sum over e to the minus beta h. I multiply and divide by q, where q is e to the minus beta h naught for my test Hamiltonian. So I've written it now as the expected value under the test Hamiltonian of e to the minus beta times the difference in those. And I can bound that as e to the minus beta times the expected value under the test Hamiltonian of the difference in Hamiltonians. This is true irrespective of what parameters are in the test Hamiltonian, so I vary those to extremize the bound. This becomes this becomes mean field if the test Hamiltonian is simpler. For example, it has fewer connections between spin variables or something like that. And then you can maximize by taking derivatives. So as a mathematician or an optimization person, you would say this is doing coordinate descent, but I simply differentiate with respect to the parameters in the test Hamiltonian, set that equal to 0, and that gives you an iterated equation. For example, m equals tanh beta m. So the free energy here has another meaning from the machine learning or statistics community called the Kullback-Leibler divergence. Kullback and Leibler, by the way, were at NSA. They were not thinking about Ising models. But this idea sort of got rediscovered at the end of the 20th century, thanks to collaboration between the machine learning researcher Michael Jordan, Tommy Yakkala, and their collaboration with Lawrence Saul, who's coming from the physics community. And that sort of launched a huge flurry in literature, 96 for the next decade, about people discovering variational methods and applying them to machine learning problems. So interest sort of exploded in machine learning, in particular in fields called latent variable modeling. The sort of spin that you don't exactly see is the latent variable. The data are disorder. And this, they simply borrowed a set of techniques for dealing with frozen disorder in the form of data for calculating partition functions. It's now a major subfield within machine learning, but the key idea remains the same idea that you learned as a young person in mean field theory. So how might we do this in reinforcement learning? So in reinforcement learning, there's a particular subclass of reinforcement learning where the necessary technical step is sampling from a posterior distribution. That posterior distribution is difficult to work with. So the problem in Thompson sampling was you actually stated a model. So I might have a case where the model of the world is actually a mixture model. So it might be, as I said, people come in 2 flavors or 3 flavors, and different types of people like different types of stuff. So how do I recommend the right stuff to the right people? So I allow that to be an augmented model or a mixture model. And then I have to differentiate with respect to the identity of this mixture, and then sample from essentially the test Hamiltonian, and it has its own parameters. So the result here is a very flexible hypothesis space, meaning a wide variety of models can be modeled. So in the original form of Thompson sampling, we said, okay, we're going to sample from P of theta given the data. Here, instead, I'm going to say, I want to find Q of theta given hyperparameters U. I want to find the values of those hyperparameters, which give me a distribution that's as close as possible to the true distribution. Close here is going to be in the Kullback-Leibler sense. And once I find those hyperparameters, then I can sample from that easier to work with distribution. You could also do this for upper confidence bound, by the way, if you're willing to integrate out the last sort of ERF, the last tail of the probability distribution. So as I said earlier, it may be that you have a mixture model in which there's a thing that's unknown to you. The sort of infographic shorthand that's used among probability community is called a graphical model. This is a picture of the random variables and how they are related to each other. The only key thing here is the absence of an edge. So when there's not an edge between 2 circles, that means these variables are independent of each other. So here in this case, I allow the true distribution in which people are of different types to be approximated by a distribution in which things are simpler. There's only one type of person, but they just have a complexity of parameters. Again, as I said earlier, this is very similar to an Ising model in which I approximated an Ising model with coupling between spins with another Ising model that has no coupling between spins, but I need to figure out what is the overall field of that Ising model. The resulting pseudocode, this is the equivalent of an m equals tanh beta m, is very simple by machine learning standards, but essentially this is what you get by turning the same crank that you would crank to get m equals tanh beta m. In the interest of time, I won't advertise too much about the experiments that show that it works. And in particular, it works even if you have a world that changes. But we showed empirically that you can get this result to work for a variety of different complexities, 2 types of people, 3 types of people. And we also showed that it works even if you need to learn from the data how many types of people are there. Essentially, the number of types of people becomes another thing over which you sample. So there's a process for doing this, which is called Gaussian processes, and for real value data, and it allows you to deal with the complex data sets. Again, in the interest of time, I don't want to spend too much time advertising how great we are, but trust us, and you can read the details that you would like. That we looked at a standard data set that's used in the reinforcement learning community, originally coming from Yahoo. So Yahoo released a bunch of data about different people clicking on ads. And this has become a useful data set for different people to benchmark contextual bandit algorithms. The other technique that we looked into was how could you leverage ideas from Monte Carlo, and in particular, ideas from sequential importance sampling. So I mentioned it's importance sampling earlier. It's the idea that you've drawn data from one distribution, but you want to compute expectations in a new distribution, multiplying by the old distribution divided by the, the new distribution divided by the old distribution can be useful, because then when you sample from the old distribution, it just becomes a reweighting of your samples. Monte Carlo, as you know, has an old idea from the late 40s, started to become in the clear right after World War II. Doing the same thing here for drawing data from a distribution where you've made previous observation becomes a dynamic reweighting over the previous observations. So what we did here is we showed that you can include the possibility that the parameters are slowly changing in time. So we wanted to see if we could have a technique where the parameters themselves drift in time. So they have their own diffusive behavior, which is really what's happening here. You can't see it, but this P of theta given theta is a Gaussian. I allow all the parameters to slightly mutate, so to speak. I will draw a sample by looking over my previous examples and weight them differently. And then I will take a new action based on what I think the world is like, based on my current sample of the parameters and the particular prior example that I've used. So it becomes simply a bigger sampling. What surprised me after doing this was just turning the crank of posterior sampling with dynamic parameters and sequential importance sampling. I ended up deriving something that's a lot like a genetic algorithm, which I never thought I would say genetic algorithm in a talk. So this is sort of an asexual genetic algorithm. You don't have the thing where genetic algorithms combine attributes of two different attempts, but you do have the thing that you take many different examples here, like a different species. You allow them all to mutate a little, and then you choose one of them to reproduce in the sense that you increase the weight of the probability you look at that particular species in the next time. And it generalizes in that you can do things you can do this as an approach to Thompson sampling, or you can do this as an approach to understand upper confidence bound, the other technique that I talked about earlier. And I don't want to spend too much time advertising that it works. You can read the paper if you'd like to see the ways that we got it to work. But it also works for worlds that are changing. So that was an important thing. Again, I like these techniques because they're very simple to write down, but also they're simple enough that you can imagine extending them to weird cases like, what if the world changes? Which again, news being one example where the world changes, not so much in like patient health, but in many cases you want to have the possibility that all of a sudden at time 500, the thing that's the best thing to do completely changes and all the parameters change, and you would like to allow them to diffuse in time, which is sort of baked into this approach to the model. Again, this is a Monte Carlo technique, so you don't actually have to know how to do calculus. Unlike variational methods where you really need to be able to actually algebraically, usually algebraically integrate out things, here under Monte Carlo, you just need to run the code and roll dice. Next steps. So those are examples of how we can take an optimization technique, reframe it in a way that allows us to write down explicit probability models and leverage statistical techniques from the great ones from 20th century. I do think there's going to be more opportunities here in health. Health is a case where you are trying to optimize outcomes. The system is very complicated. You don't have nearly as much data as you do when you have a computer playing Atari against itself, but the stakes matter. You know, you'd like to make people healthy. And as I said earlier, health, I think, is a context where there'll be more opportunities for adaptive clinical trials. And then eventually there'll be more opportunity for reinforcement learning techniques to be the technique you use for deciding the weight of the next treatment. Immunology has long struck me as a particularly interesting case for this. There are many cases where people now will do things like they'll give zebrafish a disease, and then they'll cut up their population of zebrafish at different times after they expose it to the disease and look at the population of all the VDJ recombination happening. I think given enough data, it would be really interesting to model the immune response as a reinforcement learning problem. By the way, that totally happened in the neuroscience community, decades ago when people started modeling learning, cognitive learning, using reinforcement learning ideas. I should say I've only talked today about what a reinforcement learning person might call stateless reinforcement learning. Most of the literature in reinforcement learning is about problems where you try to learn a model not only for the way that the world will respond given the treatment you give, but how the patient will move on to a new state given the treatment that you take. So these are problems in which you learn not only probability of response Y given current state X, but you also learn a transition model, the probability somebody moves to a new state given the treatment that I've given them. So that's a more complicated problem in which the response is a function of all the actions and all the states instead of just the individual IID responses. Just to give you a teaser, an example of how you might do this is one technique called policy gradient. You would like to know the probability over any possible trajectory rather than just the probability of or the policy of assigning an action given what you know. A nice technique for doing this is you treat this the same way you treat a Markov process in time, which is you work with the logarithm of the probability, so you can replace all your products with sums of logs. The thing you want to compute is the expected reward. But in order to do that, you want to find these parameter settings. That is, you need to take the gradient with respect to theta of a probability. Often it's convenient to work with the logarithm of the probability, which if you were raised a physicist, you know, because you always work with energies rather than probabilities. The expected value of the reward then involves a sum over time of gradients of the log probability, and it sort of decouples out the transition model, which is hard to learn, with the policy, which is the thing that you yourself are setting. So as you interact with the world, you only need to work with gradients of the logarithm of the probability you do something to somebody, given the state you're in. And again, for interventional studies, that's precisely the thing that you can generate more data on, because you can keep interacting with the world and sampling better and better from, well, from your own policy. Okay, so if you'd like to know more about this, we put, this is on the archive, actually a set of 4 different archive papers about trying to build better bandits. And for that, I should thank, I'm funded by NSF under a Smart and Connected Health program, in part to think about how reinforcement learning might be useful for electronic health records and medicine more generally. And that's, I think, enough time for us to dig into the Q&A. Steve, with your help.
Sorry, I had to unmute myself there. So far, the questions have not poured in.
Okay.
I think that you either explained too clearly or were too smart with what you were talking about. So
They can all go to the archive papers.
There's a question. Chase, go ahead. You got to unmute yourself. There you are.
Hi, Chris. Thanks for a very nice talk. I'm a experimental physicist, but I'm working a lot with machine learning, and specifically from a representation learning kind of perspective for model regularization and things like that. And so I don't have a huge exposure to reinforcement learning. So I guess one question that I had was, because I think I might have blinked and missed it, but these optimizations are you optimizing the exploration versus exploitation problem, or are you directly optimizing to get the best value function or reward function?
I would say more the former than the latter. You definitely are optimizing in order to get as much reward as possible, whatever that reward be, whatever that reward might be. But it's definitely the case that reinforcement learning literature, like the first sentence of almost any reinforcement learning paper, is about explore, exploit, and how you dynamically balance between explore and exploit. In fact, even as simple as what I said earlier about epsilon going as 1/t, right? Epsilon is the explore. And so by saying, turns out it works pretty well when epsilon greedy has epsilon anneal as 1/time, that's basically a way of saying that is a pretty good strategy to start out exploring at rate epsilon and then allow it to go to 0 for a particular annealing schedule in order to exploit rather than explore. I should say, because you mentioned real physics, I should say another place in which you do want to optimize like this, that is in the natural sciences, is finding the best model over parameters. So let's say you just want to do maximum likelihood with a really, really complicated model. If you have a model that's not algebraically known but has to be sampled, that is another case where you can frame that as just another optimization problem. And then you're in the world of stochastic optimization, where every time you call a function or do a simulation, you get a slightly different result, but you want to drive your parameters towards the value of the parameters that maximizes likelihood. So in a sense, you're using reinforcement learning as an engineering technique or as an optimization technique for finding the best model.
Okay, thanks. But as kind of a follow-up to that, though, because you used several times the example of the medical field and how this is really going to be an emerging application there. And in fact, I read a headline earlier today that Google is partnering with some hospital to basically, do doctor machine learning things. But you gave an example at the beginning of I- being the hospital, which just gives random drugs to random people. I mean, there's ethical implications about this too.
Amen.
Like, how does that tie in? I mean, is there some, how does this apply? Like, I mean, as a physicist, we can do experiments on electrons all day, but at some point, you can't be just doing, I mean, is this somehow a replacement for epsilon greedy? And can you say somehow that that's ethically optimal or something?
Yeah, you're not wrong. And I mean, I would say ethics is one of many reasons why there's non-technological barriers to using reinforcement learning in health. There's ethics, there's litigation and risk, there's identities of the doctors. There's many, many, many reasons that are complexifiers for trying to use reinforcement learning in health. So wanting not to go too far out of my lane, I focus today under just the bare abstraction of learning policies from health. I would say the ethical problems are real. Fortunately, people have largely worked through them in the context of adaptive clinical trials. So you're right, if you look at the literature on adaptive clinical trials, one of the things that people deal with is exactly the ethical implications. You can look, for example, at the history of the HIV/AIDS crisis in the 80s and the role of what were then called humane clinical trials, as people were realizing which treatments were effective, which essentially can be as simple as just not doing 1/K policies if you're pretty real sure that one of these treatments is going to work. But yes, in the medical, I should say the medical community is one that has worked hard at ethics, particularly since the 1970s. If you've ever worked with an institutional review board, that lineage traces to a lot of work in the 1970s to actually write a government spec for ethics. So yes, anything in the medical field, you can bet is going to be vetted by the practitioners and by the institutional review board, by the funders, for its ethical content. And yes, if you look at the literature on adaptive clinical trials, the literature is not dominated by statistical approaches. It's dominated by how do we do this in a way that's ethical, right? There's benefits to the individual patients who participate. There's benefits to the scientific community and to society long-term by doing the research well. How do you balance those wells? It's sort of an extra wrinkle on top of the ethics of randomized control trials and clinical trials. I encourage you to not shy away from it.
Chris, do we have more time with you, or
Yeah.
it's your wrap up time?
No, I can make some more minutes.
Cool. So I'm just curious, right? When you start doing these, is it a mixture of 1, 2, 3, 4 kinds? How much does that cost in performance empirically? And how often have you seen sharp answers in the real world that you get? You want 2, you want 3, as opposed to there's significant weight on a whole bunch of numbers of clusters or k-means?
Those are both good questions. It costs you, it's going to run you to actually do the sampling where you sample over K and then you think it's K plus 1 and then you go back to K. Certainly there is a performance hit to it, but it's not like everything becomes orders of magnitude worse.
Mm-hmm.
It's just, you have to keep track of a running variable, which is what is the number of states you think is real, and sample over that as well. So it's another thing to sample over.
Mm-hmm.
And in terms of whether the world works out well, that strongly depends on how misspecified the world is, or how misspecified your model is, I should say. So in cases where the world is not in your hypothesis class, you tend to learn really complex versions of your hypothesis class. Like in cases where you've said, okay, the world is only made up of if-then statements with straight lines, you tend to learn a function that's really complicated. And in cases where your hypothesis class is flexible and has diagonal lines or curves, you often sort of nail it and then you stop. So I don't know that there's a real general answer to the second question because it really depends on model misspecification.
No, that's sort of what I was expecting, but I had hopes. So we do have a typed in question about, can you see it on yours or shall I read it to you?
I can't, sorry.
So why is the Kullbacher-Leibler divergence privileged as a cost function as opposed to the Renier generalizations thereof? Seems like an ideal cost function should probably be data set dependent, but I don't know. I don't imagine it'd be easy to learn the cost function. So if it's data set dependent, that's tricky. But anyhow,
It's algebraically tractable. So
Okay.
the relative, the KL divergence or the relative entropy or the
Mhm.
expected free energy under a test Hamiltonian, they're all algebraically the same, is extremely algebraically tractable. So for methods where you have to algebraically, so when you're writing down, when you're deriving your pseudocode,
Yeah.
right? You have a cost function, you take a derivative of the cost function with respect to some parameter. It's nice if you want to do calculus to have something that's algebraically tractable. Many entropes have other advantages, including allowing more flexibility, bounds as a function of alpha, the sort of Renu parameter. Might be fun to see. A fun experimental paper to write to see how these methods change when you keep the variational inequality natures, but replace KL with other generalizations of entropy. I haven't tried that yet. But the answer to the first question is what's special about DKL relative to Renier? It's algebraically very nice.
Cool. Let's see. So I'm curious, right? Does this have, so we were on the medical stuff, you know, you always see these, like, we don't have a nice randomized clinical trial. We're going to go back and do this meta-analysis and try to pool a bunch of things, you know, some of which are randomized clinical trials. It seems like this would have implications for what you would want people to report about their studies so that the data would be more suitable for this, right? Because you need, is exactly as you say, you need some information about the population that the treatment was tried on so that you don't confuse the treatment's failure with being tried in particularly difficult cases or the treatment's success with easy cases. And I feel like the way meta-analysis in the, you know, works right now, most of what you get reported to work with in your does not have all the information that you would want for that, right? Is there some guidance here? If somebody's going to do a randomized clinical trial or a trial that's later going to go into a big pooled meta-analysis, then is there additional information that you would want them to be collecting in some standardized way?
That's a great question. So I mean, like every paper or study or data set is leaving something out. You know, every time somebody says, look, I'm not going to record a video of everybody during their interviews. I'm just going to write down body temperature.
Yeah, right. What are
Or-
the sort of summary statistics that
That's
are
right. That's right.
actually collectible, you know, in the real world, but still would give some improvement over, I don't know, nothing.
So you would definitely want people to declare what policy they were using in an adaptive clinical trial. The other thing, this is not really a statement about declaration or explicitness, but a statement about how you set up the policy. You would also want to make sure that there's some randomness in your policy because otherwise you might simply have never given the drug to a certain class of individuals, right? And you just have no training data on that particular combination of X and A, the type of individual in which treatment you gave them. So I don't know, in my experience, that's one of the more frustrating things is you'd like to learn a new policy, but you just don't have any training data where nobody ever did A to person of type X or to context of type X. But you're right. I mean, look, the more detailed the documentation is, the more reproducible the science is and the more you can learn from it. But certainly which policy was used, what pi sub minus is, what policy the bad hospital was using, it's far better to learn to know that. In the statistical literature, that is one of the problems is the weight or the inverse propensity weight, as it's sometimes called, is usually inferred from data. That can be widely misspecified. And because it appears in the denominator, small problems in the inferred policy can be really bad for your estimates of how well your new policy will do. right? I mean, dividing by 0 is bad. So the more people document not only the context that went into the policy, but actually what policy was made, that makes the data certainly more useful.
Cool. All right, let's do one more from the feed because there is a new question, which I am just going to read because it is long enough that I have not completely parsed it in my own head. So from Mike, as you probably know, animals have been reported to use matching, where they match probabilities of each possible action to the probability or amount of reward expected. But this does not maximize expected return. It is probably optimal if the world changes with time in some ways, or it could just be an easy strategy that does well enough. This is related to my question earlier, but to what extent does matching or the approach you discussed at the end of your talk depend on the accuracy of your model of the world? In particular, if I don't care how complex my mismatched model of the world has to be to match the data, then how much better would I be with the exact model? Sort of open-ended.
Oh, no, but there's a good mathy question there, which is, what are the bounds on error or regret? So in reinforcement learning, we don't talk about error, we talk about regret. How much worse did our policy behave than an oracle who really knew what to do was best would do? So you could frame that question as, what is known about the bounds on regret for model misspecification, right? So there's regret that comes from the fact that you have to learn the model while you interact with the world. And then there's other bounds that come from misspecification of the model. I don't know whether the questioner likes math a lot, but there is a great.
Mr. Mike, Deweese.
Oh, you're kidding. Oh, okay. Okay, I didn't realize that was Deweese. So look, I mean, in the abstract, there's certainly a lot of mathematical literature about statistical misspecification and how the truth being outside your hypothesis class costs you and adds to all of your errors. What can be said about natural problems? I don't know that I have a really good general answer to that, particularly now that it's Mike. So now I'm thinking about neuro context. I don't know that I have a good context for the actual working cognition and brains.
So is it?
I don't know. Let's work on that. Let's follow up offline and write a paper on that. I don't
Propose a
know.
collaboration. That would be fun.
I'd like to learn more.
Is it computationally feasible to sort of kick things up at generalization level and iterate for different specifications? So you're doing a Gaussian mixture and decay means and whatever, right? And you're iterating, the different model specifications at the same time and comparing some measure of performance and gradually narrowing down to a preferred specification.
I mean, an engineering answer is just call that another arm.
Yeah.
So,
Exactly.
so one arm draws its policy from Gaussian mixture models, and another arm draws its policy from,
Because then in some sense, right, you can try that and at least get some idea, right? If you find out that you're basically getting the same answer with 4 approaches and it doesn't care which specification, then okay, at least it wasn't that it was wildly misspecified for 3 out of 4, in which case, why do I believe I've hit the right one? But if they all work about equally well, then you're like, well, they're probably all misspecified, but there's no evidence that I should do more work on improving that aspect.
Yeah, that would be a different and interesting approach. The approach we took was use Pittman-Yor processes and allow you to sample over the possible number of the unknown cardinality of the latent variable. However, an engineering approach would be just run a Gaussian mixture model with k equals 2, 3, 4, 5, 6, and just call those more arms. Each one has its own, actions within the model, but then also there's sort of a meta arm, which is which complexity do you choose? K cross k.
Yeah.
Sorry, number of arms cross number of possible values of the latent possible actions. I suppose when you have a lot of data, you could just try that.
Yeah, and you wouldn't necessarily be limited to just all Gaussian mixtures with a big, with a big variation in n.
Right. One of your arms could be deep deep, whatever,
Yeah.
5 layers, 12 layers,
Yeah.
7 layers.
And there might be, like you said, there might be some greedy fast sort of, try a couple things. And if in fact you're seeing no variation across
Right.
specifications, don't waste your computing on this. But if you're seeing a lot of variation across specifications, aha.
Yeah, they're actually, so in many of the Bandit papers, in fact, I was saying earlier that the IGW, this very simple idea
Yeah.
from last year, works well. You can make it work even better by just throwing out results, just throwing out arms that are clearly bad.
Mhm,
So just don't even sample over the arms that are really, really bad.
mhm.
So you need to be more rigorous about what it means to be really bad. But yeah, that is one of the things that makes that is one of the sort of small tweaks that makes the IGW approach from 2020 and 2021 different from each other. So in 2021, they introduced a heuristic for not even bothering with the stuff that's clearly not working. And that actually shows up in a lot of Bandit literature, is that you can, even in distribution free cases, get better regret bounds if your algorithm is allowed to throw away things that are clearly bad.
Does seem like one of the strengths of the sort of generalization, the level of generalization you've achieved is that you could play around, as you say, by making lots of things another arm, including, attempts to address misspecification. So,
Yes.
cool. All right. I think that's about 15 minutes of questions, and I thought you had a 2:00 meeting.
Yeah, but like right before this meeting started, they canceled.
Ah, okay. Well, should we leave it there?
I think that's good.
All right. Well, it's been a
Anybody who
pleasure.
wants to know more, can send me an email.
And yeah, if you come out sometime to visit your brother, you can visit corporate headquarters here in beautiful Holiday, Utah, and maybe we'll get to take you skiing or something.
I'd love to. That's great.
All right. Well, thank you very much, Chris. Been a pleasure.
Yeah, likewise.
Bye now.